Good evening, everyone. Today I will present a topic, namely exhaustive search method for solving minimization and maximization problems. This topic is taken from a course called Algorithm Analysis and Design. First of all, I would like to introduce myself. My name is Hisham Shhade, and I got my PhD in computer science from University of Malaya in 2018 with an excellent GPA. This university is the first public university in Malaysia, which its QS world ranking is 65. My master's degree also in computer science. I obtained a certificate from Jordan University of Science and Technology in 2014 with a very good grade, which is 86.5 out of 100. My bachelor degree also in computer science. I obtained the certificate in 2012 from Al Barka Applied University, and my GPA was a 3.08 out of 4, which is very good. I worked in different universities like teaching assistant in 2013 with Department of Computer Science in Jordan University of Science and Technology. And I worked with the same department as a lecturer of computer science in 2014 until 2016. After that, I worked with Department of Computer System and Technology in University of Malaya in 2017. Currently, I work with Amman Arab University in departments of computer science and computer information system as assistant professor since 2020. My job consists of 50% academic research, 50% teaching, and 50% administration. I taught different courses like object-oriented programming based on Java, design and analysis of algorithms, C++ programming language, and other courses as well. Today, I will present a topic called exhaustive search, and we will apply it to optimize some problems like traveling salesman problem and knapsack problem. So, first of all, what is the types of problems? We have two different types of problems. The first one is minimization problem. On the other hand, we have a maximization problem. For the minimization problem, we have a set of solutions, but we are looking for the global minima, which is the optimal solution of this problem. So we may have the local minima and the global minima, but we are looking for global minima for the minimization problem. An example of the minimization problems is traveling salesman problem, and we will discuss this problem today. On the other hand, we have a maximization problem. For the maximization problems, we have a set of solution also, but we are looking for the global maxima, which is the optimal solution for this problem. And an example of this problem is knapsack problem. We will discuss this problem today also. So what is the exhaustive search? Exhaustive search is a brute force solution to a problem involving search for an element with a special property, usually among combinatorial objects such as permutation, combinations, or subset of a set. We have a set of solutions, and we will consider them all. At the end, we will find the global minima or the global maxima. So what is the phases of exhaustive search method? First of all, we will generate a list of all potential solutions. All the potential solutions will be generated to the problem in a systematic manner. After that, we will evaluate the potential solutions one by one, and we will eliminate the invisible ones. For an optimization of problems, we will keep track of the best one found so far, which is the global maxima for the maximization problem and the global minima for the minimization problems. So we will apply the exhaustive search today to solve the problem called traveling salesman problem. In traveling salesman problem, we have n cities. We are given n cities with known distance between each pair of these cities, and we will find the shortest two that passes through all the cities exactly once before we return to the starting city. So the salesman person, he will go from the starting city, suppose it A in the solution or in this example, and he will go to visit all the cities exactly once before he return back to the starting point, which is the city of A. So how we can solve this problem based on exhaustive search? So based on exhaustive search, we have a set of potential solutions, and we will consider them all. After that, we will look to the global minima for the minimization problem. Traveling salesman problem is a minimization problem, so we are looking for a global minima. If we take the first possible solution, the first choice, we can go from A to B to C to D. After that, we can return back to A. So what is the cost of this two or this path? If we make a summation for this path, for the cost of this path, 2 plus 3 plus 7 plus 5, it will be 17. So the cost of this path will be 17. If we take the second choice, the possible choice, we can go from A to B to D, then to C, and we can return back to A. So the cost of this path will be 21. At the end, we are looking for the global minima. So we have two solutions that found the global minima, which is 17, which is the minimal cost between all the possible solutions. So the global minima is 17, and we have two choices that found this solution. The next problem that we will discuss today is Knapsack problem, and we will apply the exhaustive search to solve this problem. So what is the 0-1 knapsack problem? In knapsack problem, we have a thief robbing a store, finds an items, and each item has a value and a weight. So this thief, he can put in his bag the maximum capacity of his bag. In this example, we have a capacity of the thief bag equal to 15 kilogram or 15 pounds. So he can't exceed this capacity in his procedure. So how we can solve a problem like that based on exhaustive search? This is an example. We have a set of items. Suppose we have 4 items, and the thief can put these items in his bag in different strategies. And we suppose, or we assume the capacity of the thief bag equal to 16 pounds. For the item 1, we have a value of the weight equal to 2, and the value of this item is 20 pounds. For the item number 4, for example, the weight of this item is 5 pounds and the value is 10. So how we can put these items in a maximum profit in the thief bag? There are different types of selection. We can use a set of approaches to select these items, and we can select them based on exhaustive search. And this is the topic that will be discussed today. We have different types of selecting, like we can select the higher profit of the items. We can select the items based on the minimal weight, or we can select the item based on the fraction between the profit and the weight. But these approaches related to the greedy techniques. In the other lecture, we can discuss these types of selection. But today we will discuss the selection based on exhaustive search. So how we can solve this problem, the knapsack problem based on exhaustive search? First of all, we can put just one item in the thief bag. Or we can put 2 items together in his bag. or we can put 3 items together in his bag. We have 4 items. Or we can put all of them in his bag, but don't forget that the total capacity of the item weight should not exceed the capacity of the thief bag, which means the total weight of the items should be less than or equal the capacity of the thief bag. So if we put the item number 1 in the thief bag, the total weight will be 2 pounds, and the value of it will be 20 pounds. Okay, but if we put item number 3 in his bag, the total weight will be 10, and the maximum value will be 50 pounds. If we put item number 2 and 3 in his bag, the total weight will be item number 2 and item number 3, 5 plus 10, it will be 15, and the total value 30 plus 50, it will be 80 pounds. Let us talk item number 1, item number 2, and item number 3 together in his bag. If we take item number 1, number 2, and number 3, the weight will be 2 plus 5 plus 10, it will be 17. But this weight will exceed the capacity of the thief bag, which is 16, and this solution is not visible because it is exceed the capacity of the thief bag. So we will not take it, or we will not consider it. So based on these solutions, we can find at the end the global maximum. In this solution, we found it at 80 pounds. So the 80 pound is the optimal solution of this problem. Thank you for your watching. Goodbye.